Good day, everyone, again. Welcome to today's webinar presentation. My name is Adam Harris, Managing Director for C-Therm Technologies. Very pleased to have you on the line with us today. Today's presentation is focused on application of C-Therm's sensor technology for characterizing the warm feel or cool touch of textiles and related fabric applications. Today's webinar presentation should run for approximately 1 hour. In terms of the agenda, we'll be providing an overview of the C-Therm TX Touch Experience platform. We'll be defining what is thermal effusivity, what is the principle of operation to the measurement, the Modified Transient Plane Source, or MTPS method we employ. We'll be reviewing the ASTM standard D7984, in context to measuring warm feel or cool touch. We'll talk a little bit about the touch index and what constitutes warm feel or cool touch, providing a few specific application cases. And then we'll wrap up with a comparison to Qmax, some correlation data, and finally end with a Q&A session. So it should take us the better part of an hour to progress through the presentation. I'm going to play a short video just in introducing some background material for those of you less familiar with the technology, and this will also allow a little bit more opportunity for folks to make their way through the registration process. The video runs for approximately 4 to 5 minutes, at which point then we'll pivot into the formal presentation. For the video, it is a good idea to turn on your speakers on your computer. If you're accessing the audio through the telephone line, it is suggested to turn up your speakers.
Touch. It's one of our critical senses in perceiving the world. Everything from the clothes we wear to the bedding we sleep in. The thermoreceptors in our skin monitor and relay information to our brains about everything we come in contact with. This helps us make decisions about what feels pleasant to the touch and keeps us safe. Human skin is very good at detecting differences in a material's ability to transfer heat, such as the warmth of a fleece sweater compared to the coolness of leather. This material property is known as thermal effusivity. As a metric, it can be used to quantify a textile's ability to exchange thermal energy between skin and fabric. Here's why that's important. Because human test panels have established a positive correlation between our touch perception of the warmth or coolness of a textile to its thermal effusivity. In other words, our perception that certain materials will keep us warm or help us cool down is quantifiable. We know this is important in quantifying performance in a wide range of applications, including activewear, personal protective clothing, upholstery, diapers, neoprene dive suits, and bedding. Our skin's thermoreceptors are giving us good information, though subjective. The C-Therm TCI thermal analyzer quantifies warm and cool feel for you, making what was previously subjective into a metric that can be quantitatively measured. It provides accurate measurements across a range of real-world scenarios, including higher humidity environments and under varying compressive loads. Using the patented Modified Transient Plane Source technique, MTPS, operating in accordance to ASTM D7984, the C-Therm TCI thermal analyzer directly measures both thermal effusivity and thermal conductivity. This technique determines the thermophysical properties of your sample within seconds, leaving the sample intact and undamaged. The C-Therm TCI measures the science of touch, so you can provide the comfort.
Excellent. So the video just provides a good basic introduction to some of the material we're going to dive a little deeper into today. We're going to be specifically looking at the application of the measurement of thermal effusivity in quantifying the thermal performance in terms of the cool touch or warm feel of a textile or fabric. Typically, this presentation is oriented towards folks in the textile industry that are either operating in the innovation or futures group within product development, or they're in the QC labs or material testing labs, tasked with the responsibility of quantifying performance of textiles and fabrics, tasked with testing them and generating hard data in terms of their technical performance. We'll talk a little bit about how this data is used to support marketing as well, with aspects related to claims validation, quantifying performance and how that can be incorporated into customer-facing claims on aspects of our products that differentiate it and support a premium for the product based on the technical performance. A little bit of background on C-Therm Technologies. I'm just looking at the roster and I see a lot of familiar names, but I see some folks as well in line with us that may not be as familiar with C-Therm. So C-Therm, we're a niche specialist in the area of thermal analysis. We operate in a lot of different industries, supporting clients ranging from NASA, 3M, Honeywell, DuPont. Our specialty is in characterizing heat transfer properties. That is in support of research and development, production, and quality control applications. We simplify the measurement of thermal conductivity and thermal effusivity, and that is our raison d'etre. It's our core reason for being, and what we focus on and do a very good job at in terms of offering a fast, highly reproducible, accurate method for measuring these thermal properties, and that frankly allow you to test materials under better representative conditions. A few awards we'll just talk about real briefly in passing. The technology itself has won a number of awards. The inventor of the MTPS method, Dr. Nancy Mathis, was awarded the top technical award for innovation in Canada. It's a big deal here in my country. $100,000 cash prize for the development of this single-sided sensor platform that we're going to be talking about today in terms of its application in textiles. The technology has also won the R&D 100 award, putting it in a pretty prestigious class of company in terms of technical innovation. Previous winners of this award would include developers of anti-lock brakes, automated banking machine, and the smartphone. So that's some pretty good company for us to be in terms of technical innovation. In terms of product line, there are two main product lines that C-Therm offers. The first is in thermal conductivity characterization. We have a new product launched last year called Trident that offers 3 different methods for measuring thermal conductivity. The MTPS method is also used on the TX Touch platform that we're going to be highlighting today in textiles. But I see, just based on the roster of attendees, that some of you fall outside of the traditional textile industry, or at the very least involved in other sectors such as polymers, composites, etc. So it's just maybe interesting to have some awareness of this new product. It satisfies a wide range of industry standards, ASTM and ISO methods for measuring thermal conductivity. And really, very powerful platform combining those 3 different methods for measuring thermal conductivity. But today we're going to be really focusing on the TX system, and it uses that MTPS method for measuring thermal conductivity. This is what the new product looks like in 2019. So in the video that was shot a couple of years ago, you see a slightly different design to the compression test accessory. You can see we've modernized it. It's a more compact, elegant design, more robust, different controller here from the traditional TCI. And this has really been productized around the application in textiles, specifically for measuring textiles and fabrics and the measurement of the warm feel or cool touch of those materials. some different accessories available with the system. This is an embroidery hoop that's attached to the compression test accessory and just allows for a different way of presenting the sample to the sensor. We'll get into some of these sampling dynamics as we go through the presentation, but the green area of the sensor that you see pictured here is the active area of the sensor. The fabric is brought into intimate contact with that green sensor chip, and that's where the measurement occurs. We'll be going through the dynamics of the measurement and the principles of operation here in a few seconds. So the basic specifications for the TX Touch system offers very fast measurement of thermal effusivity from a range of 5 to 1600 units of effusivity. Maybe just to explain that range, air is around 15 units of effusivity. Water is around 1600 units of effusivity. So this would cover all textiles and a range of other materials between 5 to 1600 units of effusivity. The only thing that is zero effusivity is actually vacuum. So there's really no drop-off in material testing below 5 units of effusivity. The temperature range for the sensor is minus 50 to 200 degrees C. Very easy to use. The sensor is factory calibrated. It has an internal ID chip in the connector of the sensor, which is programmed with that calibration data. And what that effectively means is that the sensors are plug and play. You plug it in, it's very quick to run a measurement. Within a few seconds, you've got hard data in terms of the effusivity of the material. No sample preparation required. It's non-destructive. This isn't going to impact the textile in any way. It's highly accurate with an accuracy of better than 5% and a precision statement of better than 1%. I'll offer just a little bit of perspective from some of our clients using the system. I think a few of these folks may be on the line today. They may be open to joining us in the Q&A session to talk a little bit more about it, but these are some client testimonials you can find on the product page from folks such as Christian Haid at Adidas and Apparel Intelligence. Just comments the device is working perfectly. Here's another one from Martin Ho over at Bureau Veritas in Guangzhou. He's the manager of their Softlines testing division. Just comments, we offer ASTM D7984. By the way, this is the ASTM number associated with the MTPS method that C-Therm developed. Martin comments that testing with the TCI in our lab, we were impressed with the service and support provided by C-Therm. So some pretty favorable perspectives there offered by Martin and Christian. There are other client statements and testimonials available on our website. And if at any point you'd be interested in talking to an existing user or in accessing some of these third-party test labs, we're happy to provide an introduction accordingly. So I want to describe a little bit the principles of operation to the MTPS method, just so we have a baseline understanding of how the method works. First off, it's important to understand what are we measuring. So the MTPS sensors measure two thermal properties. The first is thermal conductivity. And most folks know what thermal conductivity is, a fundamental heat transfer property. This can also be expressed as R value if you consider the thickness for the sample, but it's an indication of the quality of the insulation of the material or the heat conduction of the material. There is a lot of reason for why we are interested in the thermal conductivity of textiles. This can also be expressed as Clo value, or rather in converting the R value to Clo. So there is some capability there to support some of that work in terms of the insulation quality or thermal conductivity of the textile, but the bulk of our clients applying this method in textiles are leveraging it for its value in measuring effusivity. So effusivity is not as commonly understood or talked about in terms of fundamental heat transfer properties. It's sometimes called thermal inertia. It's fundamentally the thermal property that defines whether a material feels warm or cool to the touch. If you have two different materials at different temperatures coming in contact with one another, then it is the effusivity of those materials that will define the interfacial contact temperature when those two objects come into touch. So to put that more in context of what we're working with in textiles, your hand or your body is essentially a material. It's at a different temperature most often than the textile. And so it's the underlying effusivity of the textile that then becomes the variable of interest in understanding whether something is going to feel warm or cool to the touch. It's defined as the square root of the thermal conductivity, density, and heat capacity, but these are measured as a bulk number. It's not determined individually and then computed for thermal effusivity. The sensor provides a fundamental measurement of the thermal effusivity of the material. A little bit more insight in terms of what effusivity is and how it's used. So this is some work published out of the University College of London in the UK, looking at correlating thermal effusivity versus the perceived coldness of some different materials. So this was done with a human test panel where the human subjects touched different materials, different woods, polymers, and metals, and ranked them on their perceived coldness, 5 being very cold, 1 being warm, relative to the thermal effusivity of the materials. And you can see there's a very good correlation there between those two data sets. Now, the challenge with human test panels is, of course, their inherent bias and the difficulty of administering them in different regions of the world and getting good agreement between different sites, the reproducibility, the training aspects to it. So for a number of reasons, there's a lot of motivation to establishing lab-based scientific instrumentation that provides a quantifiable measurement of such properties, particularly as it relates to aspects of whether something feels warm or cool to the touch. So this index just gives you a little bit of insight in terms of the range of effusivity of different materials. So I mentioned earlier, for example, air has a really low thermal effusivity. It's only around 16 units. So air, when it's not moving, when you don't have convection, is a nice, cozy material. It's why you think of materials like down, feathers in a jacket as being quite good in terms of insulation and warm feeling. It's the interstitial air between those feathers that are doing most of the heavy lifting there in terms of providing that sensation of warmth and that insulation quality itself. There are a number of different textiles and fabrics that would typically fall in a lower range of effusivity and be associated with a warm feel to the material. So a good example would be a fleece material. Now, water, just as a point of context, has a very high effusivity relative to textiles and fabrics. It's around 1,600 units. So for the purposes of this scale, we kind of set that as the high end. Of course, if you're working with metals, ceramics, as a bulk pure material, you can have much higher effusivity than 1,600. But this is the range that we typically view as relevant for textiles, and most of the work in textiles is done under 500 units of effusivity, unless you start to look at wetting applications, which we will have a look at a little bit later in the presentation. One of the most common questions I get is what quantifies warm feel or cool touch? What is the number in terms of effusivity? And this is something that there's still some very good discussion happening within industry on. I don't think that this is fully settled at this point, but we are starting to see some consensus emerge from those discussions in terms of what qualifies as a warm feel and what qualifies is a cool feeling material in terms of the base effusivity units or numbers. Essentially, what threshold do we need to hit to really qualify a candidate material as either feeling warm or feeling cool? And so the discussions we're having with a lot of our clients in this space, we're seeing some emergence of consensus around, for warm feeling material, typically under 85 approximately effusivity units, and for cool feeling materials, typically above 200 units of effusivity. Now, different brands, manufacturers, vendors in this space will use their own internal version of this. They may have slightly different threshold numbers. They may have some adapted procedures based on the ASTM D7984 technique. The ASTM standard is meant to provide a guideline for testing, to give people perspective on how to test it consistently. It is certainly understood that within industry there is room for some modification to that, and that's typically what we've seen. It's not that different, frankly, than what we see with other textile testing equipment. For example, the Martindale abrasion test apparatus would have different operating profiles for different brands, as well as the locked-in variable sets for the ASTM and associated ISO methods for it. So there is room for some adaptation here, but I do think it's helpful to kind of have some anchor points or context to what qualifies a material as feeling cool and what qualifies a material as feeling warm. And generally, we're seeing consensus around under 85 for warm and over 200 for cool touch. If you're active in this space and interested in contributing to that discussion, I would love to hear from you. If you want to just enter a few words into the chat box on that interest, I'd be happy to revisit it with you one-on-one. In detailing a little bit further the principle to the measurement, it is a single-sided sensor that measures both the effusivity and conductivity. The active area is 18 millimeters in diameter. The way the sensor functions is there are two circuits on the sensor. There's the main coil, which is the active sensor, and then there's also around that coil a guard ring. That guard ring is very important. It is also heated electrically, as is the main coil. The guard ring guards against lateral losses of heat and ensures a one-dimensional heat flow into the sample material. I won't get into the physics of that too in depth in this presentation, but it's very important from the perspective of measuring thermal effusivity and related properties such as conductivity accurately. If you don't have a guard ring on the sensor, then your ability to measure effusivity is greatly compromised. And again, effusivity is that fundamental heat transfer property that determines whether something feels warm or cool to the touch. So when you look at the sensor, it kind of looks like a shrunken version of an electric stovetop. We heat it the same way electrically. We apply current to that coil. This introduces a small amount of heating in contact with the sample. The raw data is a voltage plot over the square root of time. A lot easier to relate to this, though, understanding that we just calibrate that voltage drop to temperature change. So fundamentally, this is really a measurement of change in temperature over time. It's that slope in the change in temperature over time that is inversely related to the thermal effusivity of the material. If I have a really warm feeling material, I'm going to have a steep rise in that slope over the duration of that measurement pulse, which, by the way, is very short, only about 1 second. If I have a flatter rise in that slope data, I am testing a material that feels much cooler to the touch. For example, something that has a higher effusivity like a metal, a saturated fabric, a ceramic, would all have a flatter slope. So the flatter the slope, the higher the effusivity, the cooler feeling the material, the steeper the slope, the lower the thermal effusivity, the warmer the material is going to feel. Now, understanding that, you don't have to interpret any You don't have to do any regression analysis. You're not asked to do that processing of the raw data. That's all done by the software with the TX system. What you're provided is a tabular output of the thermal conductivity, that thermal effusivity data you're seeking, and understanding the warm feel or cool touch of the material. The temperature is also recorded. All of this is very easy to export to the Excel. It's a very simple instrument to operate. We have had high school students that come through the lab for demo days and can operate the equipment with a 5-minute tutorial. It's a very simple system to operate and to generate reproducible, consistent data with. Okay, so let's talk a little bit more where effusivity is helpful, and we're going to pivot in more here to the case highlights. So a major area of application is in activewear and textile, performance apparel, base layers, where we care about the coziness or the warm feel or the cool feel of the fabric, both in the fabric selection and the quality control, and looking at candidate materials for different seasons, and really giving us harder quantified data in terms of technical performance of such. So a big part of it is in support of product validation, product selection, and also claims in terms of the value to effusivity. I'll give you some illustrations of, and I'm not saying that these claims are exclusively supported by such data, but these are the types of claims that this type of data would support. So here's an example of some socks saying 50% warmer than a regular thermal outdoor sock. These are the types of claims that would, this is a different example focusing more on the cool aspect or chill aspect to fabric, this one from sort of Pedic. These are the types of claims that would be supported with this type of data. And I should also take an opportunity to recognize that when we talk about thermal performance or thermal comfort, I'm not suggesting that this is a panacea, that this solves all aspects in terms of quantifying performance. There are other techniques, other methods which are very complementary and help us get a fuller picture of the technical performance of a fabric or textile. Looking at aspects such as flow, looking at other material properties of the material, how it manages moisture, etc. There's a number of different aspects to really getting a holistic view on the product performance. But what we are saying here very clearly is that if a critical performance attribute of the material relates to feelings of warmth or feelings of coolness, particularly when you put the garment on and want to ensure that you've got a strong feeling of coziness and warmth or cool and chill factors to that product's performance. And this is fundamentally the effusivity of the material, and this provides the most direct means of characterizing it. Where else is thermal effusivity useful? We have clients in the automotive composites area, so groups such as Yangfeng, automotive interiors. So when you are designing if you're an automotive engineer and you're designing the interior of a car, particularly the more you get into the luxury brands, we expect to see certain materials used in those automobiles, and they're affiliated with aspects of luxury or performance, quality, etc. So usually as a consumer, we expect to see nice wood paneling, and we expect to see leather seats, steering wheels, etc. But those are terrible materials from a manufacturing perspective, very costly. There's variability within them. They're heavy in terms of weight ratio. So for a lot of reasons, we'd prefer to use a composite or a synthetic version that allows us to achieve a better weight ratio to the vehicle, better fuel economy, can be manufactured more consistently. But the fundamental challenge often comes into, you can get these things to look the right way that they look like wood and leather, but when you get into test drive this car, if it feels like plastic, both in terms of the dashboard, the steering wheel, even the little metal accents on the knobs and door handles, etc., which are supposed to look like metal. Well, they're not metal. They're quite often painted plastic. If those parts feel like plastic, then you can bet that the consumer, whether it's consciously or subconsciously, is starting to devalue the vehicle in terms of its perception of quality. So it's a really interesting area of science, and not only looking at the the thermal performance from a conductivity perspective, but also really understanding what does it feel like and how is that going to relate to the natural version of the product. We also have good examples of Effusivity's application in baby care, so looking at diapers. When I get to some of the case highlight around wetting, I think you'll get a better indication of maybe where some of that value is, but diapers is a big business. P&G has patented some of their consumer packaging in employing the Modified Transient Plane Source technique from C-Therm. Here's an example of a baby wipes container, a U.S. patent number, and described as having a good thermal effusivity. I find this title kind of interesting. I wouldn't normally describe effusivity as good or bad. It's dependent on the application. Some cases, we want a high effusivity. If you're targeting technical apparel for summer application, you want a nice, cool feeling material. There, you're going to want to have a high effusivity. But in the winter, of course, boy, we've had a heck of a winter here in Canada. I want nice, cozy, long underwear. I want a really low thermal effusivity. So I wouldn't really agree with it being good or bad. It's really relative to the application. Let's pivot a little bit more towards the discussion on the ASTM method. So this effort was led by Marks, specifically by a product analyst, a product manager there, Shannon Yanni. Shannon did a tremendous job leading this effort on establishing the MTPS method as a D7984 test method for understanding the warm feel or cool touch, and that's a significant contribution. The ASTM standard really covers off a number of areas that are important to control for, such as defining the compressive load, the temperature, the relative humidity, and overall offering a standardized testing procedure for administering this type of test. A little bit of background on Marks. Marks is owned by Canadian Tire here in Canada. They are a retailer of different different workwear. They have their own proprietary line of thermal underwear, and I think this is where some of the interest originally started, was in thermal underwear. They're faced with the challenge, as a number of us are on this call, of selecting fabrics for different seasons, for different performance aspects, and really interested in seeing better consistency in terms of the testing of these materials for qualifying them in product selection. So these slides are taken from an earlier presentation by Shannon's group, and they talk a little bit about the value of thermal effusivity in product development, that it can be used to compare differences in the fabric's ability to exchange thermal energy between skin and fabric. Again, higher effusivity having a cooler touch and lower effusivity having a warmer touch. This enables fabric selection for summer versus winter, hot versus cold sleepers. Noted that individual comfort is related to multiple factors, including the thermal properties of fabric in contact with the skin. Important to choose fabric suitable for the intended use, activewear, where warm feel may be important to prevent chill, or cool feel to prevent overheating. Bedding is another example. Keeping you cool while sleeping is highly desirable. So this effort took a couple of years and resulted in the test method D7984. For those of you that are interested, I know that we're always looking for more participation in this committee, D13. So if you're interested in finding out more about ASTM and how to become involved, just drop me a line in the text box. I'd be happy to extend an invitation and point you as to how to register for that. The standard defines a number of aspects, as I mentioned, around compression. This is an illustration from the actual standard and just illustrates that CTA device that we showed earlier in the picture. Here are some examples of some testing done that Shannon presented, and just gives you some illustration of the values, different weights of these materials. So looking at a thermal fleece, an interlock polyester material, an air mesh polyester, and a jersey knit. And you can see the different effusivity values to these. So if I was choosing one of these fabrics solely based on feelings of coziness or warmth, I can see very clearly that the effusivity of the fleece is the lowest, and that would be the warmest feeling material. Conversely, if I wanted to select something that's feeling a bit cooler, maybe for a summer season, then I'd be leaning more towards the jersey knit nylon polyester, which had an effusivity of 184 units. Shannon noted in the earlier presentation that fabrics can be modified to provide additional warmth or improve dissipation. So these properties of the underlying materials can certainly be impacted by different techniques, such as brushing of a fabric or application of a chemical finish. In my next case highlight, I'll show an example of the latter, a chemical finish or coating designed to improve the feeling of coolness of a textile. It's noted that touch is very subjective and can make it hard to distinguish small differences in effectiveness of a modification, as where thermal effusivity measurement provides a controlled measurement to help us to better understand fabrics and their related performance. So the next application highlight came from a presentation we did earlier with Wim's group at Colortex. Colortex specializes in providing fabric cooling technologies. I know that their technology is often, I believe, applied in bedding to help improve feelings of coolness of it. So these are some example data sets provided on a non-treated, non-woven high loft sample, which had an effusivity under 75 units, and then after treatment increased it to 125. So this is used to really illustrate and quantify the thermal performance of the coating in question. Similarly, this is work done on a tubular sock material, so untreated at 120, treated, we can see an increase to about 160 units of effusivity. The last case highlight I'll speak to is a newer one in looking at wetting applications and the drying process. Now, this one is it's a bit trickier in terms of administering the test, and we are putting together a group of client stakeholders to work with us further on refining and frankly defining the process itself. Because one of the really important aspects is when how much moisture you're adding, how you place the fabric or bring the moisture in contact with the fabric, the sequencing to the first measurement. All of these are points that are really important in terms of the data generated with it. But I wanted to share some illustration as to the potential of this to look at some really interesting situations where we've got moisture added to a textile. It's a very dynamic event when you add moisture to a textile. So normally when we do a dry material test, we're typically taking 5 measurements and taking the average of them, and usually we get an RSD, a relative standard deviation on those measurements of around 1%. So it's very consistent, very precise in the measurement. But when we test a wetted material, that moisture is such a high effusivity. It's 1600 relative to a base starting point, usually in the range of about 100 to 400 units of effusivity. So you see this really steep, often starting effusivity, and then over time what you'll usually see is a decreasing effect. But it depends on the wicking ability of the material. It depends on a number of factors. So this is, I think, a really interesting area of opportunity to look at further in terms of application of this technology. So here's just a quick look at some different nylon and polyester samples that were tested. I'll just explain a little bit the test procedure that was employed in this testing. So 1 drop of water was placed in the center of the sensor. The sample was folded and placed on top of the sensor with testing surface touching. So you would typically, if you're trying to mimic a sweating example, you would typically want to make sure that if the fabric is oriented, if it's a layered structure, that you put the side on the sensor that's going to come in contact with the skin. If you were looking more at outerwear, you may want to adapt this procedure such that the water is added on the other side of the fabric. But again, whatever side is going to come in contact with the human skin, that's the side that you would want to interface with the sensor. In this particular data set that we're going to look at, the compression test accessory was used with a 500-gram force. We do also see opportunity maybe to simplify it a little bit in testing wetted materials and using more of a puck or a weight as a material to just put a little bit of compressive force and making sure there's a good intimate contact between the sample and the sensor. It just simplifies things a little bit from the perspective of testing a wetted material where it's already quite dynamic. There's a lot of reasons the CTA is very valuable in dealing with compression, but I think those are more relevant on a dry material than they are necessarily when you start to look at wetted scenarios. You want to make sure that just like under D7984 that we're monitoring the room temperature and the humidity, the relative humidity of the environment. And it is suggested to let the measurements go for quite a while. I think as we're going to look in this, I think the test time was over a half hour. I think it may be as long as an hour or even longer in duration. If you really want to look at the overall drying profile of what it looks like. So here are 3 different test sequences run on the polyester fabric sample. So you can see some pretty good reproducibility and overlay of those test results. Oh yeah, see, this test went up to 120 minutes, so 2 hours in duration. The nylon fabric was only tested twice in this case. But again, you see a pretty good, reasonable reproducibility to that profile, and it looks like they let it go even longer in terms of the testing. If we do a linear regression on those results and bringing the average together, we can use it as a basis of comparison and comparing the polyester to the nylon. So there's a few things that are interesting in looking at this. Eventually they settle out to, when the material is dry again, and that's when you get kind of this steady state effusivity of around, it looks like about 200 versus 150 units. There's a significant increase when the material is wetted. So almost a doubling of the thermal effusivity. Actually more than doubling the thermal effusivity with not a lot of water added. So that's a very significant difference in terms of how these materials feel when they are wetted versus when they are dry. But it also gives us some good insight in terms of what the drying profiles look like. That can be valuable, certainly in looking at any kind of quick dry materials, looking at wicking performance, and so forth. So I wanted to include this in today's webinar presentation. It is something that Stellar requires, I think, a further effort in building consensus with our clients and stakeholders on an appropriate controlled method for it, because it is very important to control these variables such as the sequencing of when the first measurement is taken, the amount of water added, the procedure of placing that water in contact with the fabric, But nonetheless, I think the data has great potential to add significant value for folks looking to characterize and quantify thermal performance of fabrics related to the warm feel or cool touch under wetted conditions. All right, I see we're coming up on 50 minutes. I wanted to just also wrap up with a correlation on thermal effusivity with Qmax. So Qmax is a technology developed out of Japan, I believe about 25 years ago. It is another way to look at aspects of warm feel or cool touch. We often are asked the question, what's the difference? So Qmax is another viable method for characterizing such. And speaking to the points of difference between these methods, so Qmax is used to characterize the touch property via the heat flux. It works by characterizing the maximum heat flow through a textile sample. It is approximating the same thermal property, that of effusivity. So you'll see the same units of measure represented in some of those test results. But it is done more as an approximation of the actual heat flux. Conversely, our sensor, MTPS, measures effusivity directly. Now, we would make the point that it's the underlying thermophysical property of effusivity that is what's defining whether a material feels warm or cool to the touch. The most common concern I hear raised from clients, and frankly, it's what really was resulted in us being drawn into the textile field, because C-Therm as a business has largely been focused on composites, on polymers, ceramics for the past 20 plus years, dating back to the time of Mathis Instruments, which we were called before. But it was really the challenges of the reproducibility of the Qmax method that raised a call for better quantifiable, better consistency means of measuring a warm feel or cool touch of a textile. The one thing we hear a lot in terms of comments on Qmax is the challenges of reproducibility. In a well-trained operator's hand, it can be a great tool, of course. It has been used for a number of years in industry. We wanted to give some sense of the correlation between these values. It is a little bit tricky because of some of the issues related to the reproducibility on Qmax. So if you're going to correlate to something that isn't necessarily rock solid in terms of consistency, it can be a challenge. But nonetheless, we did pursue this with our partners in China at the Shanghai Entry-Exit Inspection and Quarantine Bureau, where a number of textiles were measured, and you can kind of get a sense of the range of different textiles tested here, from linens, cottons, polyesters, etc. And this is the correlation. So not bad, 0.9334 between the Qmax value and the thermal effusivity value of the material. So generally, there's a pretty strong correlation between these methods. Qmax, again, is approximating that thermal effusivity via the heat flux, in contrast to measuring it directly with the MTPS method. The biggest point of difference is the repeatability between labs and amongst different users. Thermal effusivity measurements correlate well generally with Qmax testing values, but offers a substantially simpler method to running it with greater ease of use and speed of testing, as well as generally being more adaptable to a broadening operating conditions. So the sensor is fully hermetically sealed. It's suitable for testing water, so you can go up to 100% humidity. We have high pressure cells that have been used with the system. We offer them as an accessory. We know of clients using them, for example, on neoprene dive suits and looking at those types of conditions. Outside of textiles, we do a lot of work in nuclear and in radiated environments, in glove boxes, certainly thermal chambers, etc. So there is a very broad operating environmental range that you can apply these sensors in, which gives you great flexibility. Lastly, I'm often asked, where can I go to get some testing done with this equipment? And we're seeing a growing list of labs offering D7984. So in Asia, Intertech, TTRI, Bureau Veritas, all offer the method. In the North American side, Bureau Veritas in Massachusetts, Group CTT here up in Canada also offers it. We have a contract testing side of our business as well called TAL. We do offer also contract testing services. It's not our main focus. We do it more in support of clients looking at potentially investing in the system themselves. We're also very happy to refer clients to the third-party labs that are offering this and really specialize in supporting the textile industry. So this gives you a little bit of a view of some of the different groups that offer it as a contract testing service. Yeah, so I think that covers the items in our agenda. I will proceed to a Q&A session here shortly, but when I do that, I'm going to stop the recording and open up the telephone lines. So I just want to say thank you for taking the time to spend with us today. I hope that this content was interesting and valuable to you. We really enjoy the discussions with you one-on-one as well, and would be happy to talk about, what are your challenges from the perspective of quantifying thermal performance, whether you're in development, product, quality control, innovation, or on the third-party test lab side, and would like some help looking at this. We're very happy to support those conversations. But again, let me just say thank you. Really appreciate your time. I know it's everyone's got very busy schedules, and you taking an hour out of your schedule to be with us today means a lot. So thank you for that. Our website, there's a special product page set up for this application. It's measurewarmfield.com. You can also go to C-Therm.com and get a sense of our broader product line, but measurewarmfield.com gives you a really focused view on our application in textiles, and you can see our contact details here as well. All right, with that said, I think I'll stop there in terms of the recording, and we'll move to the Q&A session.